Welcome, everyone, to Keys to the Kingdom. This is a series where we break down some seemingly hard to understand concepts, right, into little easy to digest portions so that it becomes easier for us to remember and to apply uh, our learning into various settings for examinations. We're focusing on O-level chemistry at the moment, but we'll have Keys to the Kingdom for chemistry, physics, EMath, and AMath. This will be across levels G2 and G3, combined and pure. All right. So, okay, today my name is Thomas, and we're looking at the periodic table. Now, the periodic table is a truly underrated tool that a lot of us think we know, and ironically, we might not be using it optimally. So I put it here that the periodic table is literally our map to fighting the battle of chemistry, whether you're doing G2 or G3. The reason I say is this, there's so much information on the periodic table itself, right? And a lot of information that we can infer from the periodic table that will actually provide us a whole lot of information, right? Even a whole lot of information so that we can be able to better tackle some of the questions, right? Otherwise, we'll be scrambling for information and wondering where to find all this, right? Now, what do I mean by this? Okay, so here's a copy of a blank periodic table. And over here, right, we can see this is the latest periodic table done by 2004 syllabus. This one has been adjusted from last year, from this year, 2004. And we'll take you through the I'll take you through the various elements of the periodic table as we go along. Okay. Now, every time we see a periodic table, right, first thing we can do is to sort out where the non-metals are, where the metals are. And to do that, I draw a little staircase like that, where everything to the left of the staircase would be metals over here, and everything to the right of the staircase would be the non-metals, okay, in red. And once we do that, okay, we see that in vertical columns, these columns, they go 1 through 18, right? This is the new table format from last year, right? New table format here goes 1 through 18. These vertical columns, they're known as groups, okay? And horizontally, right, these are going across these so-called rows, they're called periods, right? And to take note that the number of periods is matching with the number of electron shells. So for chemistry, for all the 118 or so elements so far, we will say that all of them will have at most 7 electron shells. Do take note, the bottom two, those are not rows 8 and 9. Those are actually summarized. The first row at the bottom here, 57 to 71, those are summarized under period 6. And the next row from 81 to 103, those elements will be under period 7, means those at the bottom, right at the bottom, will have 7 electron shells, and those on 57 to 71, those will have 6 electron shells. Okay. Periods and groups. So all of the elements are organized by period and group, right? So right now, we're going to find the locations of these 3 elements according to their group and their period. Okay, so we're going to take some time to find potassium, copper, and phosphorus. Right, so take a few moments to find where potassium, copper, and phosphorus are located. So feel free to pause the video while you find them and list them in terms of group first and period next. Okay. Right. Hope you have some fun finding where potassium, copper, and phosphorus are. So if you know where they are, you'll find that potassium would be in group 1, period 4. Copper would be in group 11, period 4. And phosphorus would be in group 15, period 3. Right? So we can easily identify and pinpoint each of these elements according to their groups and periods. Okay. So besides finding the elements by group and period conveniently, we can also find out more about the elements according to specific groups. Okay. For our levels, we're looking at 3 main groups, group 1, group 17, and group 18. So in group 1, okay, the common name for group 1 is known as alkali metals. The reason why they're called alkali metals is because they will react with water to form alkali and produce hydrogen gas, right? So key thing to remember, they're called alkalis because when we put each of these metals here in water, they're going to form alkalis, right? Which end with OH. Over in group 17, over here in red, these are known as the halogens, right? For now, there are several properties of halogens, but we just mentioned 2 of them at the moment. So all of these are halogens, right? And we'll say that they are colored elements and diatomic molecules. So what do we mean by diatomic molecules? We're saying that each of these molecules exist as molecules containing 2 atoms only. So in terms of chemical formula, for example, we'll say that fluorine gas would have a chemical formula of F2, right? So this is important for us to remember whenever we are writing our own chemical equations. So always take note that all of the group 17s, those circled there, will have chemical formula of element name, element symbol 2. So for example, fluorine will be F2, chlorine will be Cl2, bromine will be Br2, and so on. Besides these elements, for our level, there are some other elements that usually are diatomic. Okay, these are highlighted in pink. So you've got next to fluorine, the oxygen gas, take as O2, nitrogen gas, take as N2, and hydrogen gas, take as H2. So whenever we see the phrase something something gas, right, as long as they are within these elements, chemically the symbol would be that symbol 2. So for example, oxygen gas would be O2, nitrogen gas would be N2, hydrogen gas would be H2. Right? Again, these will be important when we are writing for chemical equations. Next, we come to group 18, which are the noble gases, right? So the noble gases are very different from the halogens. Even though they are gases, with the halogens, they are diatomic molecules. I refer to the halogens as the BFF. Okay, they always go 2 by 2, buddy-buddy. But for the noble gases, they're really quite contrasting because they exist as monoatomic elements. That means they are basically like lone rangers. They just go solo, one by one. They do everything alone, right? So much so they won't really interact with their own kind. Like helium will just be happily floating helium solo, right? They will not be forming He2 ordinarily. So important things to note about noble gases that they are stable. And because they're stable, they'll be unreactive and they happily exist as monatomic gases. Now, the word stable is very important when it comes to chemistry, because when we're dealing with metals and non-metals, right, a lot of the metals and non-metals, they will react with each other with the purpose of achieving a stable electronic structure, or some of us might say a full octet or duplet structure, right? Which is the structure that the group 18s have, which is the structure that the noble gases have, okay? So for example, if we're referring to sodium, right? Sodium, when they react, they will lose their electron to form a noble gas structure similar to neon, right? So the phrasing of these is important because it's been recently updated as well. So we do need to take note that it's not sufficient nowadays to just mention a noble gas structure, but it would be much better to mention the noble gas structure and the specific noble gas structure that the element is going to achieve. Okay, with the periodic table itself, if we look at the key in orange, up at the top, it tells us that the top number is referring to the atomic number, or more pertinently, the proton number. So what this means is that how the periodic table is organized is that depending on the number of protons, the nature of the substance will change. So for example, if I'm an aluminum atom, I would have right at the top here 13 protons. But if for some reason I have increased my proton number from 13 to 14, I will no longer be an aluminum element. I would actually become a a silicon element, which has 14 atoms. So to take note that the number at the top for our periodic table would be matching the number of protons. Okay, the number at the bottom, known as relative atomic mass, is actually referring to the total number of protons and neutrons. Now, why is that? Earlier, if you learned previously, the mass, most of the mass of the atom is found in the nucleus. So we need to recall that protons and neutrons will be found in the nucleus. And because of that, protons and neutrons will be forming most of the mass of the atom. Hence, for our level, we'll say that the relative atomic mass will refer to the number of protons and neutrons in the nucleus. Okay, so based on this, can we find the number of protons, neutrons, and electrons that an aluminum atom has, and the number of protons, neutrons, and electrons an iron atom has? So take a few minutes to work this out. So here we have located aluminum and iron, where aluminum location would have been group 13, period 3, and for iron, it would have been group 8, period 4. So the way that we would find the number of protons for aluminum would be taking the top number, which was 13. Okay. And for number of neutrons, we'll take the bottom number 27 less 13 to give us 14. So an aluminum atom would have 13 protons and 14 neutrons. And for iron, if we use the same method, iron would have 26 protons, also 26 electrons. And to find number of neutrons, take 56 minus 26. Find that this iron atom, according to the periodic table, would have 30 neutrons. Okay. Now we've been dealing with atoms so far. So what's the one thing to remember about atoms when it comes to protons and electrons? So we'll need to know that for an atom to be an atom, the number of protons must equal to the number of electrons. If we ever see a particle that has a certain number of protons, but the number of electrons is not equal, we cannot call that an atom anymore. We have to call that an ion. Okay. So what type of ion do we call it? Take note that all protons will have a positive charge and electrons will have a negative charge. So if I have more protons compared to electrons, like for example with the sodium earlier, sodium ordinarily would have 11 protons and 11 electrons. Now when the sodium atom loses the electron to get a stable electronic structure, the number of protons for sodium remain 11, but the number of electrons now reduced to become 10. So that means that the protons in sodium, the sodium will have contained more protons, more positive charge, and compared to negative charge. The sodium ion in this case has 11 positive charges and 10 negative charges. That makes the sodium atom, that makes the sodium ion have an overall charge of 1 plus. And we can work out the charges for some of these groups, where I've highlighted over there. Group 1, 1 plus charge. Group 2, 2 plus charge. Group 13, 3 plus charge. And over skipping to group 15, 3 negative charge. 16, 2 negative charge. 17, 1 negative charge. Now, besides these particular groups, we'll need to take note of some of the other ions, especially for pure, but also for across G2 and G3 level. Okay, particularly, we have a few of the elements here in blue. So with the iron, it could go 2 plus or 3 plus. Okay, with copper, 1 plus or 2 plus. Okay, with lead, 2 plus or 4 plus. With these elements, we'll be specifically told in Roman numerals in bracket the charge of the ion. There are some elements where we're supposed to know what their charge is for our level. Okay, particularly with zinc, it's always a 2 plus charge for now. Silver, a 1 plus charge. Okay, and for pure, gold, platinum, and mercury, each with a 1 plus charge. And with other elements, particularly, if they ever mention other elements, they will mention the charge in brackets in Roman numerals. So we need to know, so we will know what they are if we are aware of the Roman numerals. All right. Besides looking at the periodic table in terms of the staircase, the groups, the periods, and the charges, something new that has appeared last year would be the presence of the Avogadro constant. This is what I refer to as the magic number for the moles. Okay. Now, previously, we would have to remember this on our own, but now they've put it in the periodic table, so we would be fully expected to use this particular number whenever they ask for a number of particles, right? So the number, we don't have to remember specifically, but I would say we need to know where to look for this information, which is in our very humble periodic table. The other mention at the bottom of the periodic table in blue would be something that's been age-old since our time, my time, that the volume of 1 mole of any gas, okay, at room temperature and pressure would be 24 dm cubed. So that information has always been in the periodic table. We don't really have to memorize it, but I would say we need to know where to find it, right? So this is just the beginning of how we can use the periodic table to our advantage. I would strongly recommend that we use the periodic table in this way, where we take a blank periodic table, we decorate it according to something like this, and rest assured there will be further information that we can add on, right? So I would say as we build our understanding of chemistry, we add in relevant information to the periodic table, and so we can continually look at it, on a regular basis. It doesn't have to be daily, but at least a weekly basis to take a look at how our periodic table has built over time. The purpose is so that whenever we do our WA or mid-year or a prelim, whichever, or even the final exam, the first thing that I would do is take my blank periodic table, take a minute, maximum 2 minutes, redraw it as I remember it, so that right here is the map that I can use to tackle most of the questions in chemistry. All right. So that's it for our little short section on the periodic table. Thank you very much for watching. And if you have any questions, just feel free to contact me. My name is Thomas, and I'll see you next time. Bye.